Hello, good day. We're talking about electric potential energy today. Energy is a very important concept in electricity because our appliances need energy to work. So this is your first look into what that might look like and how that might work. But of course, we have to review what we mean by potential energy, and for the next video, we'll talk about work, and then for the other video, we'll talk about work and electric potential energy. So potential energy. Potential energy is U, that's the symbol, or you can use PE if you want. And it is the stored energy that depends upon the relative position of various parts of a system. So what that means is when you have a system, or in this case our system is the bow and arrow and the girl, a system is just a group of objects that we are studying. So you can assign a certain value called potential energy, and that value will change if the relative position of the parts of the system will change. For example, these two pictures, if we compare them, we notice that the positions of certain parts of the system are different. As you can see, the arrow in the right picture is moved farther back, the spring is stretched, and as well as the bow, compared to the left picture. And in fact, for this particular situation, we can assign different potential energies. Now, my question is, which picture has greater potential energy? Greater potential energy, the left or the right? And the way you think about it to solve the problem is you try to analyze which picture seems to store more energy. And the correct answer is the right picture. You are absolutely right. And in fact, in this left picture, we usually assign this to have 0 joules because the arrow is not stretched. And for this left picture, anything higher than 0 joules, depending on the properties of the material, the stretchability of the rope, maybe let's just write a random number of 100 joules. The important thing is their potential energies are different because the position of the parts are different. Here is another system. This is composed of a mass and a spring. And as you can see, their relative positions are different. On the right picture, the spring is more stretched than on the left picture. And for this particular energy, it's called elastic potential energy, we can assign different values. And in fact, for this particular picture on the left, the potential energy we assign is 0 joules. And that is because the mass is resting on its equilibrium state. Here, the spring is stretched, so we assign it a value greater than 0 joules depending on the properties of the spring and how far it is stretched. And that is dictated by the formula right here. Maybe we just put 40 joules, right? The important thing is you assign different values because they are the relative the parts of the system are at different relative positions. Relative position for the ball is that one is higher than the other. And in this example, the system is composed of the ball and the earth. So we're actually comparing the left picture, the ball is much farther from the earth. Not much farther actually, a little bit farther when you think about the fact that the earth is so big. But the picture on the left, the ball is a little bit farther from the Earth than this ball on the right. So we, the left picture, we give it a bigger potential energy than the one on the right. The important thing is they have different potential energies because they have different, the relative positions of the parts are different. Okay. Electric potential energy is really what we are focused on. And it is the stored energy that depends upon the relative position of various charged objects in the system. Now, I want you to look at this picture. I'm sure you're familiar with this. This is two charged metal plates. The upper metal plate is negatively charged, and the lower metal plate is positively charged. And the electric field is, what is that again? Uniform, constant throughout all the parts in the middle between the plates. So each point between the plates, the electric field is constant. Now that is important because that will make our calculations easier. And as you can see, this positive charge, it will experience an upward electric field because these are electric field lines. It will experience an electric field upward, and because elect EF equals QE, this where Q is our test charge and F is the electrostatic force that this charge will feel due to the electric field. So aside from the electric field, and because of the electric field, it will experience an electric force like that. So it's wanting to go to the negative plate. But as you can see, the orientation and the relative position between the two pictures, the left and the right picture, is different. And so we can assign a potential energy. Now, I have to uh, take a step back and tell you that not all forces allow us to, not all systems allow us to define potential energies. Potential energies can only be defined for certain systems if the forces acting in that system is electric force, gravitational force, spring force, and the like. So there's something special about these forces that we can assign electric potential energies with them existing. And I'll elaborate further why these forces are important. But since here in this picture the electric force is at play, we can define what is called an electric potential energy for various snapshots, for various if there are any changes to the relative position of its parts. The system here is composed of the metal plates causing the electric field and the charged objects. And here on the left picture, the charged object is closer to the positive plate, and here on the right picture, the positive test charge is closer to the negative plate. So my question is, which snapshot has the larger electric potential energy? Or which picture shows more energy stored? Left or right? And the correct answer is left. Here we can assign, maybe here we can assign 0 joules here, especially if the positive test charge is already resting on the top of the plate because that's where it wants to go anyway. And then here, it's far away from where it wants to go and is actually being repelled by these guys. So you can imagine there's a lot of tension here or a lot of pressure here. So it has a lot of energy stored. Maybe we can assign 50 joules, right? As long as it's greater than 0 joules. Oh, that's a mistake. Sorry about that. Here, which snapshot has the larger electric potential energy? It's different now because why are these things moving? It's different now because we're now dealing with a negative test charge. So with a negative test charge, and maybe I haven't elaborated this, um, the electric field that it feels is still upward because that's what the electric field lines say. But here's the thing, it's gonna feel a downward electrostatic force. And why is that? Well, it's because of the formula QE. And if the direction of E is upward, but Q is negative, so what the negative does is it reverses the direction. So instead of F being also upward, the F now becomes downward. But what I like, so that's just what negative charges do. That's why it's more convenient to use positive test charges because whatever with the positive test charge, the direction of the electric field and the electric force is the same. But it's not that hard to remember. So again, the same here is true for this particular charge. Since the electric field is upward, its electric force is downward since it's a negative charge. It kind of goes the other way. But um, uh, unlike for a positive test charge, it goes with the flow where the electric field is pointing. But which snapshot has the larger electric potential energy, has more energy stored? And the correct answer is this guy right here. The right picture has more stored electric potential energy. So we can assign here perhaps 0 joules, especially if it's sitting at the metal plate. And here maybe we can assign 40 joules as well. Ah, don't mind the movement, that's wrong. Which snapshot has the larger electric potential energy in this case? The correct answer is they have the same electric potential energy. It seems now that what matters is just the vertical orientation of the charges. So you can see this charge is in the same height as the other charge. And I hope you guessed that since they are same distance away from the positive plate, that they will have the same, you can assign the same potential energy. Doesn't really matter horizontally wise. What matters is vertically wise. Where is it? Is it closer to the negative plate or closer to the positive plate? And here, we don't assign 0 joules. Maybe we assign 100 joules. And for here, we also assign 100 joules. They are not two different snapshots in time. They're actually, or maybe they are two different snapshots in time, but their heights are the same. Oh, sorry. Don't ignore that movement. So here, which snapshot has the larger electric potential energy? And the correct answer is the left charge. I hope you're getting it now. Right. So how do we quantify potential energy? I've been talking about, I've been assigning random values, right? I say this guy is 0 joules, the other guy is 100 joules, but we need to be able to quantify. And the correct answer is, how do we quantify the potential energy of an object at a certain for a certain orientation, for a certain relative position, is determined by the work done in moving that object, moving that system to that orientation. What I mean is, if it takes 10 joules of work to lift this ball up to this height, right, that height, then we assign that ball to have a potential energy, that ball earth system to have a potential energy of 10 joules. If it takes, on the other hand, 20 joules of work, and it should make sense, it should require more work to lift an object that high, higher than compared to the middle ball right here. And we can assign for the bottom ball 0 joules because you didn't really need to lift that up because it's already in the ground. Sometimes people just do that. Whenever an object is in the ground, then they assign it 0 joules for gravitational potential energy. So you're lifting the ball. if if it takes 20 joules of work to lift this ball up to this height, then you assign a potential energy of 20 joules. So basically, potential energy is just equivalent to the amount of work that you put into the system, the amount of work you spend in changing the orientation of the objects in the system. So, right. So for example, my cell phone here, it's resting in my palm. Can you see? I lift it up. That means doing work. And by lifting it up, I spend maybe 5 joules of energy. And so therefore I can say that the new potential energy is 5 joules higher than the old potential energy. So potential energy and work are related in that manner. But I've been using the term work, and so for the next video, I'm gonna help you recall what work is. For that, let's look at this picture. So electric potential energy. Now, originally, this guy, the positive charge is right here. And I had to apply external work because it has to be external work because naturally and normally, this charge will not naturally go closer to the positive charges because it doesn't want to go to the positive charges because these positive charges are naturally going to repel it. So I had to do some external work to lower this charge so that it goes to the positive plate. And if I spent 20 joules to do that, then this guy now has 20 joules of potential energy. Right. So that's just how potential energy works. I hope you had learned a little bit today.